In the last video, I defined the natural log of x as definite integral from 1 to x of 1 over t dt, and some of you guys may have been astonished at how weird this definition is compared to a seemingly easier definition of log base e of x. And in this video, I'm going to show you these two definitions are exactly the same thing. And how can we show these two definitions are exactly the same thing? Let's think about what log base e of x represents. Log base e of x represents that this function is inverse of e to the x. Log base e of x represents the exponent you get when you raise something to e power. So log base e of x represents this value. So log base e of x is doing opposite of e to the x, or it is the value you have to raise e to get some value y. So if we can prove that log base e of x is inverse of e to the x, or that definite integral from 1 to x 1 over t dt is also inverse of e to the x, then we're done. Then we have shown these two definitions are equal. And how I'm going to do it? I'm going to prove the natural log of x to the nth power is equal to n times natural log of x using this definition of natural log, and I'm going to expand upon it and show you that e to the natural log of x is equal to x, and natural log of e to the x is equal to x. And if these two things are true, then you know e to the x and natural log of x are inverses, because f of g of x and g of f of x are the same. No matter which one you evaluate first, if you plug it into the other one, you go back to the original value, and that's the definition of inverse function. So we're going to start with proving this. Then we're going to prove this, and we should be done. So let's do the hard part. How can you prove natural log of x to the nth is equal to n times natural log of x? Well, let's think about what derivative of natural log of x is to begin with. Our natural log of x is defined to be integral from 1 to x of 1 over t dt, and you may recognize this from second fundamental theorem of calculus, and this value is precisely equal to 1 over x. You just replace x with t. You just replaced t with x, I meant to say. So the derivative of natural log turns out to be 1 over x. That's good to know. Now let's try to differentiate natural log of x to the nth. Well, let's let x to the nth to be our x. So we have 1 over x to the nth. Now you gotta differentiate x to the nth. So you have n times x to the n minus 1. Just doing the chain rule. And you have n up top and you have 1x down below. Because you have one more x in the denominator compared to the numerator, it comes out to be n over x. How about n times natural log of x? What do you get when you differentiate it? You get n times 1 over x, or n over x. So realize, derivative of natural log of x to the nth and derivative of n times natural log of x are the same. What's that telling you? It's telling you these two functions only differ by constant. So what that's telling you is natural log of x to the nth can be represented by n times natural log of x plus c. And I'm not going to formally prove y in this video. Maybe I'm going to prove it in some other video. I think you have to use mean value theorem and some smart tricks to do it. But let me show you intuition on y. Consider x squared and x squared plus 1. When you differentiate this, you get 2x. When you differentiate this, you get 2x. And you can see that they differ by constant. They differ by plus 1. So in this case, since derivative of natural log of x to the nth and n times natural log of x are the same, they differ by a constant. So now let's try to find this constant. Let's let our x be 1. What's natural log of 1 to the nth, which is just natural log of 1, times 1 times natural log of 1 plus c. Natural log of 1 is 0, or you can subtract natural log of 1. Either way, you get 0 is equal to c. And this thing is telling you natural log of x to the nth is exactly equal to n times natural log of x. So we have proven our first theorem. Now let's show natural log of e to the x is equal to x, and e to the natural log of x is equal to x. Let's start with this one. We have just proven natural log of x to some power. You can bring this power down. So we're going to do exactly that. You're going to get x times natural log of e. And by definition of E, natural log of E is 1. So this thing is equal to x. So we have the first one. Now let's look at the second one. Let's let e to the natural log of x be some number a, and I'm going to show you a is equal to x. Let's take natural log of both sides. So we have e to the natural log of a is equal to a. Next, we're taking natural log of both sides. Exponents come out. So you have natural log of x times natural log of e, which is 1, is equal to natural log of a. And if you think about natural log function, it is 1 to 1. For each value of y, each value that you get when you natural log something, there's only one value of x that corresponds with it. So if you plug in x and a to natural log and get same y out of it, that's telling you the input must have been same to begin with. So x is equal to a. So e to the natural log of x is equal to a, which is equal to x. So we have proven both of them. So we are done. So what did we do? Let's review. We started with this definition of natural log, definite integral from 1 to x of 1 over t dt. We use that to show natural log of x to the nth is equal to n times natural log of x. And using that, we proved that e to the x and natural log of x are inverses by showing this thing and this thing. And in the end, that's showing you natural log of x is equal to log base e of x. So these two definitions are precisely the same.